This program is a presentation of UCTV for educational and non-commercial use only. Check out our YouTube original channel, UCTV Prime, at youtube.com/UCTV Prime. Subscribe today to get new programs every week.
Professor George Smoot was co-awarded the 2006 Nobel Prize in Physics for discovery of the black body form and anisotropy of the cosmic microwave background radiation. Dr. Smoot received his bachelor's degree in mathematics and physics and PhD in physics from MIT. Dr. Smoot has been at the University of California, Berkeley and the Lawrence Berkeley National Lab since 1970. In April 1992, George Smoot made the announcement that the team he led had detected the long-sought variations in the early universe that had been observed by the COBE DMR, NASA's COBE, the Cosmic Background Explorer. This is a satellite that mapped the intensity of the radiation from the early Big Bang and found variations so small they had to be the seeds on which gravity worked to grow the galaxies, clusters of galaxies, and clusters of clusters that are observed in the universe today. These variations are also known as relics of creation. Professor Smoot is an author of more than 200 science papers and has also published the scientific book Wrinkles in Time that elucidates cosmology and the COBE discovery. As founder and director of the BCCP, a cutting-edge cosmological research and education center, Dr. Smoot also leads the Global Teachers Academy, where high school teachers and students from Paris and Berkeley learn about 21st century science through cosmology and frontier researchers. Currently, Professor Smoot conducts research in astrophysics and observational cosmology and is the most famous for his research on the cosmic microwave background. Today, Dr. Smoot continues research in cosmology and is currently involved in the Planck and Euclid missions. The Planck mission is the third-generation mission to exploit the CMB fluctuations discovered by COBE DMR. Euclid is a mission to understand the dark energy causing the current expansion of the universe to accelerate. Professor Smoot is active in other areas of research and with collaboration and collaborators is preparing a satellite to observe gamma-ray bursts, which are the most energetic events occurring in the universe from the formation of the first stars up until the present day. Please welcome Nobel laureate George Smoot.
Okay, well, I only have a little bit in Spanish. All the talk mostly is going to be in English. You see a picture of what you should be able to see over there in the dark, except we have some lights on here instead of over there. But I'll ask you a quiz about this building in a minute. But this picture was taken when people were allowed to go up the steps. We have an award for people who have the best talk and the best posters at our school. And so we were thinking those are the ones that should get to go up and be sacrificed. But we'll see at the time. Okay, I wanted to show you one other thing. That it turns out I've been here a number of times in reality and in virtuality, and I came here almost 3 decades ago for the first time and was really awestruck by the place. And so we'll talk a little bit about the place and then we'll get on to what modern cosmology is about. But for some years, I've been on the board of directors of the Chabot Observatory and well, it's space science. It's a science and education center, and the then director of the observatory got a large grant from the National Science Foundation to make a new planetary show, which eventually became El Universo Mayo, or if I could speak Mayan, Yok Okob Maya. And in English we made it Tales of the Mayan Skies. And it had its world premiere in October of 2009. And part of the deal I had thought was we would actually get a place for to be able to show the show here, because what we did with the grant, which was quite a substantial grant from the National Science Foundation, was to come to Chichen Itza with laser interferometers and measuring devices and actually map the entire site to better than a millimeter in most places, but better than 2 millimeters over the whole site. And we were able then, I didn't come for that part, but we were able to then to reconstruct in the computers and in the planetarium this place so that we could simulate the solstice and to simulate the planets going over and the stars going over, and let people in other places live that situation. And unfortunately, we ran out of money before the planetarium show was finished, and but our new director raised money, so there is a planetarium show. Unfortunately, it isn't here, but you can see it in Mexico City and in many other places. So there is both a Spanish version and an English version of the show, and I recommend you see it. But we did have the world premiere in Mexico City in 2009, and so since then you should, if you get a chance, get the opportunity to see that, and you'll see the whole history of the Mayans' concept of how they came into existence, and what the role the Great Ball Court, which is not so far from here, played in it, and how the twins defeated the gods and established the Mayans and allowed them to have what goes on today. And it's a very interesting story. But so though I didn't get to come here in person, I got to visit virtually and see the final product. Unfortunately, in the budget cutting to make the planetarium show, which now makes money, they cut the people who could run the simulated show. So we have all of Chichen Itza in the computer, but we just can't show it anymore. So, but anyway, that's a side issue. Hopefully that will be recovered at some point. Okay, so I'll remind you what they said, and make you jealous that people used to get to walk up and down those stairs, even though it's pretty steep and dangerous. The Mayans tinkered with the calendar, and they did a lot of things. And you heard from the previous speaker how the calendar actually got shifted a little bit over time. But the basic calendar was a 52-year cycle, and what that meant, there were nearly 19,000 unique days, which can chronicle a person's life. But many people will be born someplace not at the boundary, so that you would need a couple of the basic calendars in order to do it. But the Mayans were very interested in, very focused on the fact that there were cycles they observed in the sky, and we'll talk about that briefly in a minute. And so they thought everything was cyclic, so they had a calendar that eventually had a long count, which is the 5,126 years, with the starting point, which people think is equivalent to August 11th and 3114 BC, which on the Gregorian calendar, because you have to talk about which calendar. And so on the Julian calendar or the astronomical calendar, it's a year later, September, a year later. But anyway, the implication is that the end of this cycle is around 2012. It's around now, but the transition into the end of this world cycle, into the new world cycle of precision cosmology, is only roughly around now. But we're here celebrating it now because the 12s came up on the board. It was like the zeros coming up in 2000, where 2001 was the beginning of the century. 2000 was much more fun to celebrate. So that's what we're here. So, all right, for the quiz, did you notice the star rising? Have you looked up away from the lights and looked up and see the stars rising? Did you notice a relationship to the Castillo? If you were watching, some of us, at least where I was sitting, you could just barely see the star at the edge of it, and now you see it going up. Did you notice any relationship between the arc the star is making and the building itself? So if you looked carefully, you will see the star is rising straight parallel to the face. The face that the stair or the snake comes down, which on the equinox has the serpent that crawls down, and it has to be that way. You had to have made the building in that way so that on the solstice you would actually get the light creeping down the stairs one after another as the sun rose or sunset, so that you would eventually come down and connect to the head, because it has to be lined up exactly east-west. And so you can ask yourself, how could the Mayans know that? And then how could they build a building lined up east-west? And they built on previous knowledge, and they did just what we do, which is they have built very careful machines, in this case buildings, like here in the Caracol, which I'll talk about in a minute, which allowed them to make more and more precise observations, and then make more observations over time and record exactly, count the days and count the events to things recycled. So the Mayans had already inherited the knowledge and built it themselves. They knew that the stars make this big arc across the sky going east to west, or west to east, depending on which way you think the things are going. And they also noticed that the sun's track in the sky made that kind of an arc, but it moved north and south in the sky over the period of the seasons. And so they understood that there were special days when the sun would be lined up in a certain way, either the solstice or, in the case of this, the equinoxes, which there would be the special cases. And but in order to build the tools to measure that more and more precisely, or to have the ceremonies to celebrate it, they actually had to build this building with incredible accuracy, right? And they're not the only ones. You'll notice the pyramids were lined up quite that way. But you also know they have a limited data set because they didn't really understand about the precession and equinox, right, which is a more 26,000 year period, which there's some hints that they had an idea about it, but that's longer than the database for which they were working. But the key issue is they were building on previous knowledge to construct new devices that allow them to make the more precise measurements so they could build and refine their calendar and make it better. And that's a very similar kind of thing that we do today. So the Caracol building, so in the picture in the top left, but you see here's the pyramid and here's the Caracol, which is the other major observatory, which astronomers know to be the observatory because it's the round domish kind of shape. But part of that is due to the ruin, because if you actually go and look at it carefully, you'll see it was actually a cylinder. But you'll notice they built the building very specially. They built it so they could measure the summer solstice. So this building has stairs for the number of days, and it also is lined up to celebrate the equinoxes and so forth. But the Caracol was designed to see the summer solstice and also the northern Venus setting, right? So they actually had a double use for this building. And they were using Venus, one, because it was a bright object in the sky, and two, because its timing happened to be correlated with the rainy season, which told them when Venus got to a certain point, that was time to plant your crops, the beans or the whichever kinds of things that you were needing to do. And so this building had an outer part which was designed to see the solstice and also and the northern Venus setting, and the winter solstice and the summer sunrise solstice, right? The building is set up like that. So if you actually went by that building, look carefully, you will see there were external features and internal features that allow that to work out. And the thing that I hadn't seen before, but I saw today, was up in the top, there's actually a little cubby hole which looks a lot like the prime focus at the 200-inch telescope. In the bad old days, and astronomers had to crawl into a cold cage and hang up there motionless in the middle of the night, because if you moved around it would shake the mirror. It's a tradition that's been going on for a couple thousand years here. Okay, so when you were looking at the pictures and you're looking at this thing, realizing these stairs, this entranceway and so forth, actually had astronomical meaning. And there's an observer up here, but there's observers out these doors. And so let me show you the other sort of setting on this building, where the focus was on Venus, where there are various places to stand and edges. If you go there, there's little places marked in there, so that when you look out, you see the sunset at equinox, you see the northernmost point of Venus. There's little places marked where you go and see, and you look out through the windows and through the edges, and you will actually see these things. And because there's little edges and marks, it's much easier for you to make the measurements and see what's going on. And so this is the Mayan symbol for Venus, and this is the god known as, there was a symbol for Venus. But this shows you that sort of the principles of rational reasoning and building the foundation for science have been around for a very long time. The scientific method, we think, is a relatively new invention, but in fact, people were working and building and doing these kinds of things, and it's very similar to the kind of things we do now to build our new tools in order to understand the universe. Okay, so now I want to go on and talk about how we're able to go out with instruments now that augment the human eye. They were using the human eye and just using buildings and objects, but they're still using the human eye as a sensor. Now we've gone past that to where we're using all kinds of new detectors as sensors. So we extend the range well past the visible, and the sensitivity out to incredible regions, because we can make many more detectors than you can line up eyes and so forth. So we have a bunch of things that we do where we can go out and investigate the universe and try and understand what's going on, including going back to look for those relics of creation. That is, using instrumentation that allows us to look at things that our eyes can't possibly see, but that tells us something about the universe. And so we had the Hubble Space Telescope as an example of an observatory that we put up into space. You've seen this picture a couple of times before in the previous talk. This is one of the Hubble Deep Field pictures. And in this picture, we see something that the Mayans couldn't see. They could only see at most 2,000 stars from this site on a beautiful night. You can see a planet there. You can see many stars up in the sky in that way, as long as the light aren't too bright in your eye. But I can see a planet. I can see a couple of stars right up above us. But if you look in this picture, almost everything you see, there are 4 stars in this picture, but I've cut 2 of them off of the screen here. Everything you see in this picture is galaxies, and you see some galaxies that are big and have unusual shapes. They're spherical or spiral galaxies, but there are lots of smaller galaxies. And you think, well, they're smaller, that must mean they're further away. Well, that's partly true. They are further away in general, but they're more irregularly shaped. But the thing that was a surprise at the time when these pictures were being discovered, and about the time these pictures were first being made, was that they are blue in color. And we already knew by this time the universe was expanding. We expected the galaxies that were further away would have their light more redshifted. They should be more red, but instead they were more blue. It was already telling us that galaxies and then had stars in them that were hotter. We now know, in fact, stars were forming much more vigorously and much more massive stars back in those days compared to the later days that we live in now. We're in a period of less star formation, and therefore less bright stars than we are in this period. But when you look at this picture, a lot of questions come to mind. Well, how do the galaxies get there? Why are there so many galaxies, right? And how do they evolve over time, right? And those are the questions that the Mayans never asked, because they didn't know there were galaxies beside our own. They only knew of the Milky Way. They didn't know if it was a galaxy or not. But now we know that there is something on the order of 100 billion galaxies in our observable universe, and we know that we need to study them and understand them so we can see if our ideas of where they came from are correct. Okay, so we have a primary tool. Sorry, this used to be in Spanish, but I replaced it. I gave a talk in Russia, and I cut the Spanish out and put a Russian words on there. But we have a tool that allows us to have hope in doing that, and that is the universe is so big that even though the speed of light is very, very fast, when you send your flash off, the light comes to me and back to you before you could blink your eye, or before I could blink an eye, so you have to have a red eye on your camera. But for the universe, that's not the case. Light coming from the sun to us takes 8 minutes. Right? It takes a second from the moon, but it takes 8 minutes from the sun. Well, 8 minutes isn't that big a deal, but I could blink easily in that time if I knew you were taking a flash. And 8 minutes only matters if you think there's a big solar flare coming and you want to set down your radio stuff so it doesn't get damaged. But when you look at the nearest, say, 50 stars, the average travel time is like 10 years. Well, if you're getting a picture of the star with that light that comes from there, of what the star looked like 10 years ago, but a typical star in our galaxy is anywhere from 10,000 years to 100,000 light years away, and therefore, when you take a picture of it, you're seeing what it looked like in a much more distant past. But the nearest big galaxy to us is Andromeda, and it takes light 2 million years to go. If you were in Andromeda and you had the best telescope in the whole galaxy, and you took a picture of the Earth, you would see no evidence of mankind. There would be no Chichen Itza. There would be no Mayans. There would be nothing, because as far as we know, there were no men 2 million years ago, right? That we were just getting to the point where there might be men. And so there would be no signs of civilization, and you would think, well, there's nothing intelligent on the Earth. There's some life, but there's nothing particularly intelligent. And this is kind of the phase we might be in. We're discovering extrasolar planets, and we're going to get some indication that some of them have life on it. But many of those things are going to be thousands of years in the past. right? Or millions of years in the past, depending on how far out we're looking. Right now we're looking only in our own galaxy, so it's in the thousands of years, but that's the kind of time scale we're talking about. But if you go out to typical galaxies, then you're talking billions of years to tens of billions of years. And if you go out as far as you possibly can, back to when the universe was 1,000 times smaller, 1,000 times hotter, then you're back to when the universe was essentially an embryo, and that's where the cosmic microwave background comes from. So that's what we spent our time on COBE, and then WMAP, and now Planck, mapping more and more precisely. And so the good news is Planck is working great up until this weekend. We ran out of helium-3 this weekend, so the high-frequency instrument on Planck is beginning to warm up, so no more data. Well, what that means to the people, many of the people in the audience, is it means we have 1 year to get our data out, data analysis out, because the data becomes public in a year in principle if we can get it all calibrated. So, you know, knowing Planck, the papers will come out just before the data comes out. But, you know, at least finally we're going to be putting out some of the cosmology papers, even though a lot of the astrophysics papers are already coming out. So you have to bear in mind in this picture, the beginning of the universe is the sphere around us, which is roughly 14 billion light years away, and the present is just where we are, right? Because we're looking around. You can imagine around us at the present, there are the 100 billion galaxies around and everything else, but we only see them through light in general, and that light takes a finite time to get to us. So what we do is we look back in time, we see out to a broader and broader part of the universe. Okay, so to recap, we're in a spiral galaxy. We're in a spiral arm in the spiral galaxy, and there are concentric spheres around us in distance, but they're also concentric, rings around us in how long it takes the light to get to us. And so around us, there are very many modern type galaxies, spiral galaxies, elliptical galaxies, and so forth. But when we go further out, we start seeing these irregular shaped galaxies that are bluer and have ferocious light in it, or some hidden off the edge here that are doing that way. But there should be a lot more galaxies in the picture. So here's the picture that shows the cosmic spheres of time, that we're here in the center in the present, and as we look back out in time, we see modern galaxies, and we see earlier galaxies, and we see the very beginning galaxies. And then there's the dark ages, which we haven't detected much from at this point. There's a transition region, which is back sort of at the dawn, where the first stars and the first compact objects are being created. And there we occasionally get some information, but it's pretty rare to this point, though new experiments are being done to do that. And then we go back to where we have this incredibly detailed map of almost the very beginning of the universe at 380,000 years out of its 14 billion years. And we see these very tiny fluctuations, which are really only about a part in 100,000. And yet, in the present universe, we see huge voids where there's almost no material at all, and then the matter all clumped up into galaxies and gas clouds and so forth. And so part of what we have to explain is how the universe get from being very, very uniform with only this small patchiness. And when I say small patchiness, if you know what a billiard ball isn't as round and smooth as the universe was at that time. And it's like a glass of water has some irregularities in it. The universe had irregularities in it, sort of similar to the kind of irregularities you see in a glass of water that's very still. This glass of water has little ripples on the surface just from me moving around and talking that are much greater than these kind of variations that we were talking about. Okay, so I mentioned we had 3 cosmic background missions over the time. There was the COBE mission, which was launched in 1989. 11 years later, we had the launch of the WMAP satellite, which has been operating up until last year, so it got 7 years of data. So we had 4 years of data, 7 years of data. And now the Planck satellite, which was launched in May and began taking 2009, and by the fall of 2009 was in position and was taking data over 2.5 years. And now one of the instruments is being phased out, and the other will run on for a while longer. But the bulk of the cosmological interesting data has just been taken, and so that processing is going on. But we're going from sort of a coarse map to a finer map with more wavelengths to a much finer map with more wavelength and better measurements of the polarization of the microwave background. And we hope they're telling us very much about what's going on in the embryo universe, so that we can understand a starting point and see how the universe might develop over time. But we have to understand, we have to take snapshots at different distances so that we have the sort of the time history of the universe that we can compare against our models and see how things are going. Okay, so here's a little animation of Planck, and this is showing actual data coming in from the sky from the first year of data. Now we have 2.5 years of data. And so this is the third generation one. It's arranged so it's far away from the sun and the earth, so they're in the back of this thing. And then the antenna receives the microwaves and millimeter waves from the far sky, and as it scans around, it starts to build up a picture. So you see this picture. This is a multi-wavelength. There's 9 different wavelengths, so this is a multi-wavelength color picture. You see a band across here, which is our own galaxy. So this is the actual scanning pattern. So we scan around, and in 1 year, actually in 6 months, but in 1 year when you throw away the holes made by some of the planets, you get this whole map. You unfold it so it looks like that, and you move it over where it's in galactic coordinates. You can compare that to what you get in the optical, where you see the dust and the stars, and then what you see now. And so that's the map we have. We now have a second map equivalent to that, plus another half map equivalent to that. And from that, we've made up this brief history that we're testing against that map to see what's going on. Where if we look at the present time, we see the galaxies and the modern galaxies around us. We're here in the center, right? And we assume these are here, but we're looking back, sort of on these diagonals, 45 diagonals. And where light's traveling, and we're projecting forward, that around us are these sort of modern galaxies. As we go back, the galaxies are the more primordial galaxies. They're only just forming way back here at about 400 million years after the beginning of the universe. And what we do is, this is the part, all the part we can see, so this should have the 100 million galaxies in it. What we see is there's an accelerated period, and this was a discovery made in 1998. And accepted pretty uniform by sometime in 1999-2000, pretty well accepted, and was actually the two groups that were doing that. The leaders of those two groups were awarded the Nobel Prize this year. Well, sorry, last year. It was in December. Were awarded the Nobel Prize for the discovery that the universe is accelerating. We had thought the universe was slowing down under gravity, so still expanding but slowing down, but in fact it's still expanding, but expanding more and more rapidly. And so this is one of the new surprises. So we call this dark energy as the cause, but what we observe is accelerated expansion. And here we also know that there was the development of the galaxies, the stars, and the planets going on, and that's kind of interesting. Somewhere roughly in this same epoch, our solar system and our Earth formed, but we now think it's extraordinarily likely that even back here stars and planetary systems were forming, and we know there's still some stars and planetary systems being formed at the present time. So it's a continuing process. We're sort of somewhere in the middle of that process in terms of what's happened to formation of our solar system compared to earlier solar systems and more current later solar systems. And as you go back further, we eventually get to the dark ages, which we're just beginning to think of ways to explore in some serious way. And then we have these detailed maps from the cosmic microwave background experiments and the 3 large satellites. But then we know we can extrapolate further and further back. There's still a period of slowing down, but we think that somewhere back here very early, there was inflation, and everything, all those 100 billion galaxies and everything that we think is in the universe today was once back in a place that was smaller than an atom. And that's a very good packing job. Then how do we know that, and how do we think that? Well, we're doing observations and we're doing tests, and we're trying to figure out how is it possible to put everything together, get these tiny quantum mechanical fluctuations and have them grow over time to become the fluctuations we see in the microwave background, and then grow over time to become the galaxies and clusters of galaxies that we see today. And then test our theories against the observations we have. So, whoops, sorry, I went too fast. So here we have the beginning of large galaxy surveys. So this particular one is a picture of the Sloan Digital Sky Survey, where they take pictures like the Hubble picture pick the things that are galaxies, estimate the distance to them. You have the angular position on the sky from the picture, and then you make a plot. And as the Earth rotates and you take a series of pictures, you get fans across the sky. And if you tip to a different angle, you get a different fan. So here's a movie that shows sort of the shape, and I'll show you another one later. But this just shows you the shape of where the location of 1 million galaxies are. And the thing that you notice about it is it's far from random in the normal sense of just throwing darts at a board and seeing a pattern that they appear. It's in fact, there's clearly correlations. There are regions where there are almost no galaxies, and regions others where there's lots of galaxies together in groups, or in this one case, the Great Wall of Galaxies, which is swinging around, and we'll see come around on this side, right? This section right along here, called the Great Wall of Galaxies. And one of the things that people try to do calculation statistics are is how likely is it that something like the Great Wall of Galaxies should appear up. There it looks like a string, but there's more. I'll show you another survey that actually shows you this is actually a whole sheet of galaxies, not just a wall. So here's a fly through of the 2-degree field of view. And you can see the database that we're building up over time. So, we had people that did computations for Maya. I didn't mention they used base 20 for the most part, and so they made interesting choices in their calendars that was different from the Gregorian counting calendars. But here you can see we have a database that not only has the location of all the galaxies, but has information about each galaxy. We know its color, we know whether it's spiral, elliptical, we know a lot of things about it. And here you can see again the natural geometry, the fan shape you get when you do a galaxy with a ground-based telescope and just take pictures, or you go from one location and you spin around, you take a series of pictures, you're going to get a fan shape kind of pattern across the sky. And you can see over here to the left of center, you can see part of the Great Wall showing up in this survey too, even though this is a different slice that's that way. The Great Wall isn't just a complete sheet, but it is a kind of a sheet of galaxies that's more clustered in one place than in other places. Okay, and so that hasn't stopped. Sorry, there are now just released last week the first results from the Sloan Digital Sky Survey 3, which is generally known as BOSS, because now we're looking for the baryon acoustic oscillations in a sky survey. But this is the Sloan Digital Sky. There was 1 million galaxies in the first 2 surveys, roughly each, and in this survey, Sloan 3, they're trying to measure 1 million galaxies per year. And so this is the data from the first year, but the second year data is already in the can. But you can sort of see the kind of a pattern that's beginning to show up on the sky. So this is the sort of luminous bright galaxies. And so this is still new, so they haven't made a video of this yet, but there will soon be a video of this, and we'll see. But we'll see in a minute that this is extending out to much deeper into the universe than we had been doing before. Okay, so and while BOSS is going on, we're making plans for Big BOSS, and so some of the people here, some of our colleagues are involved in this, and you can see the inner region, which was the original, this little red region here, which is the original 1 million galaxies, and this is the region that BOSS will go out to, and this is the region that Big BOSS will go out to. If we stayed on Moore's law, we should get to 50 million galaxies, but right now I think that we're only in a position to get to 20 million. But if you can do 20, you can do 50. But you're really starting to do that, and then you can use quasars and use the light from the quasars. And if you can get the spectra done very carefully, you can actually look at the intervening material, gases and stuff between them, and study some more. So not only do you get this sort of wedges much deeper and much further out, you can go even further with fingers that are sticking out. And here you're talking about something on the scale of 500,000 to 1 million quasars, adding these little filaments to the survey and giving you this additional information. And so we hope that this is in operation by 2015, and then by 2020, right, the end of this decade, we'll be in the position where we've expanded things by another huge factor. Okay, and so now the question is, how did we get from the early universe to the late universe? And the answer is, we've got to use the physics that we know and the observations we know from the cosmic microwave background, and then put that in and do simulations, right? Because it's complicated to do the theory. You do simulations with computers, and you use the tremendous power of huge arrays of computers, and you try and simulate what's going on. So here's a small simulation of using just dark matter, another one of the things that were necessary, we found, in order to explain the universe, that there's a whole new kind of matter, unlike the matter we see around us here, unlike the building blocks that the Mayans used. And that dark matter just will clump it under gravity. First you'll see spots, and then you'll see those spots are connected together in filaments. And they make a kind of a web, which the ordinary material that makes up stars and galaxies, the stars that we see showing up as individual stars and in large groups as galaxies, fall into those potential wells. And because they can dissipate energy, they fall like sediment to the bottom of the tub or the bottom of a stream, and you see them in the center of the potential wells in terms of what's going on. So this is a simulation just of what the dark matter looks like, going from the time when the universe was 20 times smaller up until about the present time, and you see the things going on. And that's about as far as you go. The size of this box is such that if you were looking for larger scale structure, the dark energy causing the universe to accelerate, or whatever is causing acceleration, would actually cut off the formation of even larger scale structure. But there have been even bigger and more impressive kinds of simulations done, and when you look at them at the sort of the end, at the present time, you find that if you look on the large scale, the universe looks very uniform, but as you zoom in, it looks very irregular. And in fact, you'll realize that it looks like some biological systems you see, or some things like the carpet of grass that looks very uniform from far away, but when you look at it closely, you see the details. So here's the Millennium simulation, and 1 gigaparsec, 3 billion light years. And you see, from far away, it looks very uniform, but as you zoom in, you start seeing structures, and the structure isn't that regular, it's kind of random, and it has filaments and voids, and there are places where the filaments come together, and you get a lot of stuff. And here, white is the dark matter, and yellow is the ordinary matter that's come to form stars. And of course, you zoom in on the largest and the presumably rarest thing in there, a place where many filaments come together, and therefore a place where you expect the sky to be full of galaxies, this to be a huge, rich cluster of galaxies. Now, as we zoom in further, you'll see two little spots in here that are sort of under the M in the megaparsecs. You see two little spots. They're about as far away from each other as we are from Andromeda, that is 2 million light years. If you lived in this galaxy cluster, no matter where you looked in the sky, if you could sort of shake your head around, you would see galaxies the way when you're in the southern hemisphere, you can shake your head and look out of the corner of your eye and pick out Andromeda. You can sort of see that. Now, it's great to have these maps, because when you have maps, you can kind of see what's going on. But if you're in the middle of it and you're driving around, it's not quite the same. So here's a drive-through. Remember, white is the dark matter and this kind of puffed up halo, and then the yellow are the stars, the things that have been able to lose energy, dissipate, condense in the center of the potential well, like the dirt settling into the bottom of the bathtub, the lowest part in the potential well. And you can see the hints of the filaments, and you can see the halos of the dark matter that's around the ordinary matter. But when you're in the middle of it, it's much less obvious about what's going on. It's only when you pull together a whole map that you begin to see these patterns. So the maps give us an idea about patterns, and the maps versus distance give us an idea about the time history. So we're seeing geometrical patterns when we look out at a given radius, and when we scan across radii, we're seeing the development of the universe with time. Okay, so here's another simulation. This was done by some of our colleagues in Korea with their friends from Princeton. And what you see here, if you're here now and you're looking back and out along this sort of three-dimensional light cone, is you go back to the very beginning, you see the universe is warm but very uniform, and as time goes on, as you get closer and closer to the present, you start seeing the structure form the way it did in the simulation, until you get down to the present time, you see very sharp edges and very unique kinds of things. Okay, and here it is without all the labels on it, so you can see it again. See how smooth it is back when the universe was much smaller and it was much younger, and then how the structure forms and becomes more, the gradients become much higher and so forth. And what you're seeing is we're starting from a universe which is very uniform and very much sort of set by sort of random fluctuations, and we're seeing the linearity of gravity produce correlations and phases and link things together in a very serious sort of way. Okay, so we have the map on the top, which is, the map from COBE, 4 years of COBE with a model of the galaxy removed. And the map on the top on the right is the map from the WMAP satellite. We haven't released the one from Planck, but it will happen within a year. And below is a picture of the Earth in the same resolution. And you will see there's a difference between the COBE map and the low resolution map of the Earth, but it's not overwhelming. It would be hard to tell. But if you look on the right, you will see there's a huge difference between the WMAP and the Planck map kind of resolutions between what the Earth looks like and what the universe looks like. And that's telling you that the formation of the structure on the surface of the Earth is very different process than the formation of structure in the universe at the beginning. That is, in the bottom picture, you can see long features with sharp edges, right? Like the Mid-Atlantic Ridge, like the edges of the continents, like the fault lines that you see in the Pacific Ocean on either side. Those are strong evidence of nonlinearity, because you can't get a sharp edge like that that's continued over a long distance unless you couple the phases of very short wavelength objects with middle wavelength objects with long wavelength objects. But when you look at the top map, you don't see any sharp edges like that. And that's telling you the forces that form space and time were very linear compared to the forces that formed the surface of the Earth. And so, in principle, it's the savior for cosmology. It's easier to calculate what happens in the universe than it is to calculate what happens to the continents on the surface of the Earth. And so that's part of the thing that we're looking to and looking forward to, and trying to understand what's going on in the universe. And we're down to the point where we know that the formation of the fluctuations in space and time, and in the making of the space and time, and in the distribution of material, there was extremely linear kind of process. It's when gravity kicks in that we started to get the nonlinearities and the sharp edges starting to form. But it's more than that on the surface of the Earth. It's more than gravity that's causing these sharp edges. But gravity is certainly an important feature in what's going on. Okay, so now we're going to take a little flight through the universe. So we're starting in the solar system, but I won't show you. I'll show you a picture in a minute of going by the planets, just because that was interesting, because that's what we could do 10 years ago, but now we can make this picture. So every one of these stars that's in this picture is a star whose position we know and whose brightness we know, and is traced very well. And you'll see there's a very large number of stars. It's more than 500 million stars there, but that's not enough. You have to go and do a French Impressionist painting in order to show the whole Milky Way, because there are 400 billion stars in the Milky Way, and so a billion is less than 1 in 400, right? So you only map a tiny fraction of it. And then you can see the other galaxies around us. We in Andromeda are large galaxies, so I'll show you something with a better quality in a minute. But this gives you an idea of the kind of a situation that we're living in and where we are, and how far we have to go from our small local group of galaxies before we start getting around to other galaxies around us. So we're not living in a big group of galaxies. We're one of two big galaxies in a small group of galaxies, and then you go a long way before you start running into other galaxies. And they're not even big galaxies at the beginning, and then they get to be bigger. And you go faster and faster. And then you get out to where things are not complete. You remember the maps sort of fall off on galaxies. It's because the telescopes aren't big enough to see dim galaxies. You can only see the very brightest galaxies. You can only see large red luminous galaxies and quasars out to the greater distances. Now let me show you a movie we made a year and a half ago. So it starts from the highest point in the Earth. And one reason you do that is that the Earth looks impressively spotted and mottly and so forth. But from the highest point to the lowest point on the Earth is 28 kilometers. And the Earth's radius is 6,000 kilometers. So it's apart in 2,000 at best. So when you get further away, the Earth starts to look round. But when you're up close, the Earth looks really quite varied and quite rough. But when you get the further and further away you get from the Earth, the more like a sphere it appears. And what you have to remember is the universe as a whole is much more uniform than the Earth is, right? The surface of the Earth is much rougher than the early universe. And look, there's extra moons. And you'll recognize the near-Earth orbits, and then there's a white line coming across here. That's the geosynchronous orbit, which is the geosynchronous orbit is effectively full now. And then there are the Molina orbits, which the Soviet Union and Russia preferred for a lot of reasons. And so there are still a few satellites up in those orbits. So there's the geosynchronous orbit. And that's the moon. And now you see the Earth's orbit. And Venus, which they spent a lot of time, tracking here. And then Mars. Well, you guys have all seen pictures of the planets. But actually, there's been a lot of progress in studying the moons and the planets in details. And here are the zodiacal constellations, again in the ecliptic. But as you go further away, you'll notice these distort because what you think is a constellation depends upon how close to it you are, and whether the stars are actually tight together or something else. That's as far as radio signals have come from humanity, and that's about where we've looked until the Kepler for almost all the planets we've seen. Kepler is looking at another patch on one of the other spiral arms, so there's two spheres roughly that size that we're looking at. So here's the nearby galaxies. And you'll notice there's some places where we don't map galaxies, and some places we do. In part, we don't map there because our own galaxy blocks our view by having dust and so forth. And then you see we run out of telescope power to see the typical galaxy, but we can see the really bright galaxies and quasars much further out. The new surveys are extending how far we can see more regular galaxies, but are also concentrating on the brightest galaxies. And then you see out to the most distant sphere we can measure with light. Now we get to go home. And so there's a story the astronauts tell that when you're on the moon, you can hold your hand out and cover the Earth with your thumb, and all you see is blackness. And this picture just before, when I said that, you could hold your thumb out and cover our galaxy, and all you see is blackness. So the scales are immense when you start thinking about the universe, but they're telling us something about how different the early universe was than the present universe, and about how complicated it is going to be to figure it all out, but how we have hope because the early universe turns out to be much simpler than the present universe. So we need a version of this that zooms in on Chichén Itzá, but unfortunately, the place we picked was the highest place in the world. And even the Chinese might have objected to that. So this is the data from Google Earth, so you can actually remake this part if you want. And there's Google Earth on a cloudless day, which is made by taking many pictures together and just excluding the parts that have clouds until you build up a picture that doesn't have clouds. And here you can see the pattern. You can see the Himalayas being one of those large linear features I was talking about. Okay, well, maybe that's enough. You guys feel safe back to Earth now? Okay, let me skip on and show where some of this data come from. So what you see, that movie was made by pasting together data from many different sources in order to, and we didn't use everything. We didn't use the billion stars and so forth. But this is the latest movie the Sloan Digital Sky Survey released. Before we just, there's no movie of the new release that was released last, at the AAS meeting. But this one has all the 500,000 galaxies and this nearly 100,000 quasars. So you're flying out. But you can see how large the databases are we're talking about and how serious we're doing the mapping. And it seems like, 50 million galaxies, which is our next goal, or 5 million galaxy, which is on the way. That seems like a lot, but when you think that it's like 100 billion galaxies that you could survey, you realize you've got your work cut out for you, right? So there's jobs for cosmologists for a while longer. Even if we stay on Moore's law, right? There's at least another 100 years of observations to be made. But here you see sort of a prettier picture of that earlier, survey that I showed you, where you can see the wedges and you can see the voids, right? You can see the pattern of how the sky scanning is done, how much more is left for us to do. And then you can see the large luminous galaxies and the quasars, and finally the cosmic microwave background. So we've made improvements, and by making these improvements, we've gotten people interested enough to make things with high production values now. So not only can we make this two-dimensional representation of a four-dimensional object, we can now get movies that give us, three-dimensional representation of a four-dimensional object, and that we're on the way to really doing a very serious trying to map the history of the universe, right, both in space and time, in order to truly understand whether we're on the right track or if there's some additional hidden features that we don't know or understand about. So I think I'll stop at this point and see if there's questions, or some people want to volunteer to climb the pyramid.